So we have some key ideas about how CPUs work that are crucial for performance in modern systems. Caching, that is, getting some values from memory faster than others, particularly ones that we just recently used, and speculative execution to get a head start, even though we don't know which way some branches are going, while we have these minions run around in parallel. Again, it's speculative execution. It can do things that should not actually happen as far as the program can observe. And that includes things that shouldn't happen because there was a bounds check in the original program that made sure that we didn't try to walk off the end of the array, so a minion working speculatively might actually go fetch a value past the end of the array that it's not supposed to. Similarly, we might try to access an address that we don't actually have access to, that page protection is going to reject, but it's possible that the minion goes out and gets the memory anyway before the page protection check completes. So these things that should never happen because they were guarded by branches will not be visible to the end program directly because speculative execution makes sure it doesn't actually execute, it doesn't commit to those changes until it's sure that it has taken the right branch. So the program will not see those speculative changes except to the degree that it affects timing. And this is our side channel that can expose information about the state of memory. We now know enough that we can set up our attack. Here is a new program. It has some elements that are like the sum program, but we're starting from fresh to build our attack to read parts of memory that we're not supposed to be able to see. We do that by creating an array that is 256 elements, and it's an array of pointers where each pointer points to some different page. By different page, I mean something that's fetched separately by the memory system and on different pages from the OS perspective. We're going to use those array of pointers in a probe function. So probe takes two arguments, an integer indicating whether it should do some check, and then an address that it should try to read from. In the attack, this address is going to ultimately be one we're not supposed to read from. But at first, we call probe with addresses that we can read from. To start the attack off, step one is to call probe many times with true for the check argument and a good address for the second argument. The point of calling probe many times this way is to convince the branch predictor that this if is going to succeed, and so if it's going to speculatively execute one of these two branches, it should start reading out of the address and looking up an indirection through that result. You don't have to call probe very many times to convince it that this check is going to succeed every time. Step two is to read a lot of memory that's not the pages referenced by my pages. The point of this step is to make sure that none of the pages that these pointers refer to are cached anymore. So if we do try to read from one of these pages, then that will affect the cache, and we'll be able to see that through timing. Step three is to call probe with false instead of true and the address that we want to attack. Because check is false, we should not try to read from the address. But because the processor has been trained that the check will succeed, then it will speculatively look inside of this address, even though we're not supposed to be able to see inside that address. Maybe we're not supposed to see this address because it has virtual memory protection that we're not allowed to see, or maybe it's off the end of the array and corresponds to some other memory in a safe language like JavaScript. The JavaScript variant of this attack involves not just making up raw addresses, but using an address and an index that is out of bounds for that address. That would have been guarded by a check here, but we've trained the CPU that the check will succeed, that the index is in bounds. In any case, the effect of this is that a byte that you shouldn't see at this address is read speculatively. From the C perspective, it doesn't matter because you're never going to see that index and you're never going to see the result of looking inside of my pages. But since speculative execution will use those index and try to read through a pointer in my pages, it turns out it'll bring exactly one of these different pages that are referenced by my pages into the cache. So 255 of my pages are still out of the cache. One of them is in the cache, and the one that's in the cache now corresponds to this byte that we should not have been able to read from adder. Step 4 then is to read a byte from each pointer in my pages and time how long it takes to read each of those bytes. If the byte that we try to read is already in the cache, that must mean that it was pulled in by speculative execution, and that would tell us the integer that we got. So whichever of these steps, whichever the 256 pages is the fast read, the index of that page is exactly the byte that we read from memory. So that's the essence of both Meltdown and Spectre. In the case of Meltdown, the byte that we were not supposed to be able to read, we weren't supposed to be able to read it because the page protection, as implemented by the page table, is supposed to prevent us from grabbing that byte. But if the byte is actually grabbed before the page table check happens, then that means we were able to read a page that we shouldn't have been able to read. Similarly, in Spectre, a bounds check or a tag check was supposed to prevent us from reading some bit of memory, but due to speculative execution, the memory read happens anyway before the bounds check is completed, and so again, we see the value of some memory that we should not have been able to reach.